Hi, good evening, everyone. Am I audible and my screen is visible?
Yes, sir. Yes, sir.
Okay, thank you. So let's wait for 5 minutes and after that we will start. Anybody is like facing any issue regarding Aspen installation now, or everything is all right? Please confirm, students. Please confirm about Aspen installation. Do you have access to Aspen now?
Yes, sir.
Okay, thank you. So if you have access, then I request you all, please also open Aspen window. So during this class, we will try to do some sample problems. So maybe it will be good if you also do same in the class.
Okay, sir.
Yeah. It will be good for you. So it will be a good learning experience. So we can do it together actually. Yeah.
Question about assignment question. I already solved 5 questions, but the acetone problem, there is a vapor phase cracking. So I'm not able
Actually,
to.
sorry to interrupt you. Uh,
Yes.
we will not discuss the current week assignments. Okay. So actually, don't discuss any question about week 3 assignment.
So
So the
I need guidance in a just a I just want one simple base method. It is already given in the question, but in
okay.
my B 12.1, it is when we are doing take a base method, then it is not correct. Yet it's giving error anything else like this.
Okay, if like normally in question, I think they have already I think specified the which method you have to use. So maybe go through the question again, read carefully which method they have mentioned, or maybe like you have to select some other component also because like if you are using like RK method, then you have to change the steam. You have to change the steam table for like steam NBS. You need to use that like that actually. Normally, some methods we use steam TA. So maybe that kind of things you need to change. So carefully go through the question, or if you are having, if your inputs and everything is okay, then you can also look into the method assistant. So do like that, or maybe next week. So please, you can email me that question. So you have my email ID at the end of this slide or on the previous week's slide. So you can email me. So next week we will sure discuss that. Okay. Okay, let's start.
Sir, one question. A warning
Yeah.
in a
You are not audible.
NRTL binary parameters for all components pairs are 0. It's showing like that.
Okay.
Result may be.
So see, so I think in the week 1 class for binary instruction parameters, you need to make some changes. You need to I try to go through week 1 classes. So yeah, if warning is regarding the binary parameters, then you need to select an option. So I can't tell you that option. So you have to go through the week 1 classes, then only or next week I can tell you because we are strictly like we cannot discuss current week assignment question. Sorry.
Okay, okay. Okay, thank you.
Yeah. So okay, so we have waited enough. So let's start today's class. So good evening, everyone. I welcome you all to the live session number 3 for course Aspen Plus Simulation Software, a basic course for beginners. So the course instructor is Professor Prabirkar Kumar Shah from IIT Guwahati, and I am his TA Amit Kumar Sharma. So today we will discuss week 3. First, we will go through the course summary from the previous week, and then we will have some sample questions. So we will go through that, and those questions will be very helpful you in your assignments. Okay. And this session is being recorded. So, and the recording of the session will be provided to you with this PPT from the NPTEL team. I think you already received the link for that. So in that you can find the this PPT and the recording after 1 or 2 days. Okay. And also, like if you have the Aspen in your computer, so I request you all please open that Aspen, because when we will solve the question, then it will be very easy for you to do that. And from this week, I think we will complete all the basic modeling, like the simple models. Then from this week onwards, and in this week also, I think the professor also discussed a complete flow sheet. So from now onwards, I think there will be more question like that only, the complete flow sheet solution. So in this live session also, we will try to do that kind of problems actually. So it will be better if you have access to the Aspen in these classes also. So let's start. So in week 3, we covered about the reactors, the pumps, and I think a basic complete flow sheet. Okay, so just start with the reactors. So the reactors are basically three types. So one is the balanced, then equilibrium, then kinetic. Okay, so in balanced reactor, like R stoichiometric, then R yield, and in equilibrium based, R equal and R Gibbs, and kinetic R CSTR, R plug, and R batch. So these are the basic in the reactor. So you can see these in the model palette. So we have separate individual model for these kind of reactor. Each reactor have their like specific work. Okay, so we will discuss briefly, and then we will go through some examples. So in the stoichiometric block, the models with the specific extent of reaction or conversion. So if you know the conversion, you know all the stoichiometric, so you know the conversion, then we use this kind of block. Then model where the reaction kinetics are unknown, you don't have the reaction kinetics, okay, but the stoichiometry is known. So you know the stoichiometric coefficient and all the stoichiometry, but you don't know the reaction kinetics. Then we use this block. It performs product selectivity and heat of reaction calculation. So important, like what is the funda for solving behind this reactor. So it performs the product selectivity and heat of reaction calculation. It can run either simultaneously or sequentially. This is about the stoichiometric block. Then the R yield block. So it does not need kinetic or sizing information. For R yield, we don't need kinetic data, okay, and we don't need the sizing information. Then here you need to choose like the mole basis or mass basis. So in mole basis, number of moles of the chemical living through the outlet per total mass of feed, and the mass basis like mass of the chemical living through the outlet per total mass of feed. So you can basically you can define the like how much mole or mass will be leaving. So based on that, it will do the conversion. So R yield satisfy the total mass balance. So it is based on the total mass balance, not the individual component balance. So it gives a warning message that say it's scaled up or down. The molar mass balance is that the total outlet mass flow rate is still equal to the inlet mass flow rate. So it is based on the total mass flow rate to total mass balance. So the inlet flow will be equal to the outlet flow. it as such does not satisfy the first law of thermodynamics. So it is not satisfy, it doesn't satisfy the first law of thermodynamics. So important, it does not satisfy the first law of thermodynamics. And R equal. So this one is useful for modeling a reversible reaction. Okay, reversible reaction, assuming that it achieves chemical and phase equilibrium. So you have a reversible reaction and you will assume that it will achieve the chemical and phase equilibrium. So from the name itself, R equal, so it based on the chemical or phase equilibrium. It calculates maximum thermodynamically possible conversion one can achieve based on the reaction condition. So it will go for the equilibrium, then it will like the maximum thermodynamically possible conversion. Okay, it is wise to use sub-equilibrium condition at an approach temperature. We can also define the approach temperature. Okay, computes the equilibrium constant directly from the Gibbs free energy of reaction at temperature of reaction condition. So you have defined the conditions. So based on those conditions, it will calculate the Gibbs free energy and do the equilibrium calculation. It calculates the output using equilibrium coefficient combined with mass balance, energy balance, and flash calculation. So important, it will do the calculation using equilibrium coefficient combined with mass balance, energy balance, and flash calculation. It requires separate outlet ports for liquid and vapor. So because it is based on the all chemical and phase equilibrium, so it will try to show you all phases from that equilibrium. Okay, so maybe the some will be liquid or some will be vapor. So based on that, it require separate outlet ports for the liquid and for the vapor. Then the R Gibbs. So it does not need to specify the equation. So if you are using the R Gibbs, then you don't need to specify the equation. Given infinite time for reaction, chemical equilibrium is achieved when the product mixture reaches its lowest possible Gibbs free energy. So you don't know the reaction. You know that like my system is having like carbon or hydrogen, or they will do some reaction, okay, at high temperature. So there will be some combustion, okay. From that combustion, maybe different kinds of gases will be there, but you don't know like what are their like kinetics. So which will like comes in first, okay. So you don't know all the data. So similarly in reforming also, like if you are having methane, you are having CO2, you are having steam. So there can be steam methane reforming, dry reforming, like reverse water gas shift reaction. Depend on water gas shift reaction depends on temperature. Maybe methane cracking. So there can be different kind of reactions. Okay. So you don't know all the reaction kinetics. So but you know the input. So based on that, with the temperature condition and the pressure condition, so it will take the infinite time of reaction. So it will assume the infinite time. Okay, it will assume the infinite time, and it will reach the chemical equilibrium, and it will show you the all possible phases. Okay, and when it's the at lowest possible Gibbs free energy. So this is the Gibbs block, and through a complex algorithm, our Gibbs block solves an optimization problem that finds the exact outlet mixture which has the lowest possible Gibbs free energy. So it will give you the exact outlet mixture which has the lowest possible Gibbs free energy. And the first law of thermodynamics holds in this calculation. So it's also the first law is also valid here. So you can use this Gibbs block for the calculation to find out the possible outcome from some uh, input. Okay. So let's take an example. I think this example was also discussed in the class. So in this, you can see we have a reactor. Okay. So it is with the this reaction is water gas shift reaction actually. So in this, the carbon monoxide will react with the steam and will convert into hydrogen and CO2. You have given the temperature, you have given the pressure, okay, you have given the flow rate, and you have given like 92% conversion of CO for stoichiometry and R yield and 253 approach temperature for are equal. And you have to use the Peng Robinson equation of state with Boston lattice property methods. So I think you all have tried this. Just I will discuss it quickly. Let me open my Aspen. Okay, I think my screen is visible.
Yes, sir.
Okay, thank you. I think someone is unmuted. Please mute yourself. Okay. So here I have like all the reactors. Okay, here. So we have feed, then we have a duplicator. So we have supplying the same feed to all these reactor. Okay, and we will see like how different options are available in each reactor, and is there any like what kind of things we can do with this. So if you want to see the inputs, my screen is visible.
Yes, sir.
Yes.
Okay, okay. So let me make it a little bit zoom. I think now it's better. Okay. So on the left side, you have all the like items for in the simulation. Like you can see the block B1, B2, B3. You can see all the results, and at the bottom you can see the result summary for all the results. So first go to the properties. If you want to see the inputs and methods, so first go to the property, then the components. If you go to the components, here you can see. So the component is H2 of water, carbon monoxide, carbon dioxide, and hydrogen. So if you see from the question that we have given a reactor and we are doing water gas shift reaction, we have given the flow rate, okay, the flow rate of carbon monoxide, the flow rate of steam. So here you can see the output, okay, and we have given the data for these two reactor and this reactor. So for this only these inputs, we will model this for the all reactors. And let's see. So these are the inputs. So if you go to the methods here, so if you see in methods, we are using Peng Robinson. Okay. So with Boston Mathias modification. So we have given this, like this is the method we have to use. So I think somebody was having doubt regarding like here you can see the for petroleum calculation option we use free water method. So we have like steam table correlations we have here. So we have different kind of correlations. Sometime if you are using a particular method, then we need to change this free water method also. Okay. So please check this. Maybe the issue is with this. Then you will next. Then you go to the. So this is the property. Okay, we have specified the components. We have specified the method. Then if you press the next button, then you can go to the simulation. So go to the simulation now. So here you can see at the bottom we have the reactor pellet. So we have here our stoichiometric yield equal Gibbs CSTR plug and batch. So if you click on the feed, click on this, so you can see the input. So the temperature 360°, pressure 1 bar, then the mole flow 500 and 100. And one important thing actually is sometime some student make mistake here. Actually they put the total flow rate here, okay, and also here they want to give the mole fraction, but they forget to change the composition, like the option here. Actually, if you're giving total flow rate here, like suppose if I give it 100,000 here, okay, and if I change the here the mole fraction, so I want to, like suppose if I have total flow rate is 1000, okay, and the H2O is 50% and CO is 50%, then I want to give total flow rate at this location, total flow rate, then I will give the mole fraction here like 0 0.5 and 0 0.5, then it will divide this flow rate in half and half, okay. But sometimes you forget to mention the mole fraction and you like click here the mole flow, okay, and you see the unit is kilomole per hour, then you will enter 0 0.5 and 0 0.5, then it will take this data, okay, and maybe you will have warning or sometime it will run and you will have different results. So be careful with this, it should be in the sync. So what was the flow rate here? I think it was 0, so we have given only here the mole flow rate, right? Let's check it in the question. So yes, it's 100 500 CO H2O, okay. So to mention this, then you can go to the, you can click on next. Then the duplicator, you know that it will just duplicate the stream. Then let's go to the stoichiometric. So it will have one input and output. You can connect multiple inputs there, but it is the feed only, like it will be the input is only here and this will be the output. You can connect multiple streams, okay. The temperature 360, 1 bar, also the valid phases. So this is option is important. If you specify the vapor only, then this will result in only the vapor phase, only the liquid phase. So it's better to have vapor liquid because the temperature range is 360, okay. But it's always better to have vapor liquid if you are sure that your output will only contain vapor or liquid, or like it is if it is mentioned in the question that you should have like this phase only, then you need to specify it. So you can have vapor and liquid here. Then the reactions, to go to the reaction, then you can see here we have a reaction here, okay. So just click on edit. So because we have already reaction, I have entered it already. So the left side is reactant, right side is product. So the reactant is the steam and the CO. Then the coefficient of -1, okay. So it's the stoichiometric coefficient. Minus is because it's a reactant, and here the plus is for its product. And you see the -1 because if you see the reaction, then it is CO, 1 mole of carbon monoxide reacting with 1 mole of steam. Suppose if it is 1 CO and 2 H2O, then that coefficient will change. So that will be -1 and -2. Okay. So the coefficient is the stoichiometric coefficient of the reaction. So okay. So put -1 and 1 1. Then this is important. So the product generation. So the fractional conversion. So here select to specify the fractional conversion of reaction. So here you need to specify like how much of your input will be converted into the output. Okay. So basically like you have specified 92% of component CO. The meaning of this is that the 92% of CO will react with the steam and convert into hydrogen and CO2, and remaining 8% of CO will not take part in the reaction. So you have you have mentioned the conversion. So this is the conversion. Okay. If you like suppose here we are only having one reaction. But in the if you have like multiple reaction, like you are using, if you are having combustion, so in the combustion there can be multiple reactions. So you can add more reaction by clicking on new. So here you can add like you need components. So if you have multiple components, then first you need to specify all those components in the property segment. Okay, in that segment you need to specify the component, then you need to identify all their properties, then they will appear here. So here you can select the component, select the coefficient, then you can select the products, and you can do the this calculation. Just because here we only working with the water gas shift reaction, so we only have the one reaction, we don't have two. Okay, but you can add multiple reaction, and you can also see the reactions occur in series. So like if you know, like first this reaction will occur, then second this reaction will occur, then third this reaction will occur, so you can also click on this option. So then the reaction, this reaction number is important then. Okay, like if you know that your reactions are like happening in series, particular series, because if one reaction will produce some product, then only the second reaction will occur, like that, and you know that, then you can select this here also. Then we have some other options also. So because see, we have selected reaction number 2, but we have not entered any data here. So you can see here this blue tick changed into the red, so it requires input. So as we have only one reaction, just delete it. Delete. Now it's again turned to blue. So these are the basic inputs, but if you have more data, so you can go to the like combustion, heat of reaction. Okay, so there are more options. So you can also choose selectivity. So you can go through the manual and you can find like how can you further like advance the this reactor, and how many more inputs you can give to the system. So this is about the stoichiometric reactor, and if you run it, then we can see the result. So let's go to the result. So this is the B1. So if you go to the B1, if you go to the stream result, so yeah, so our one is input, then P stoichiometry is the output. So if you see, so see the mole flow. So the CO was 100% at the inlet, and we have given 92% conversion. So now you can see at the output 8% CO is still there, because the 92% will take part in the reaction and remaining 8% will left without having any reaction. Okay, so this reactor stoichiometry is only good when you know that you have this much of conversion. Okay, then it's important. Okay, so you can see the H2 is 92%, CO2 92, and steam is 408. You can also see the temperature, the phase, vapor phase. So both are in vapor phase. Okay, and like we have selected vapor and liquid, so there is no liquid. Okay, if there is any liquid, then we can see, but you can see the temperature and all, so both are vapor, but still we have chosen vapor and liquid. Okay, so this is about the stoichiometric reactor. Now let's go to again the flow sheet. Now this one is yield reactor. So for C, we have given for the 92% conversion for stoichiometric, and also for the R yield. So now let's see. So what are the options available in this reactor? So yeah, in this also the specification, you have like two option here, temperature, pressure, because we have given that only. But if you have given something else, like if you have given duty, you have given rarefaction, you have given temperature change and all, so you can select from these four options. Okay, but we have given the temperature and pressure, so we are choosing these two. Then the valid phase will be vapor, liquid. Okay, then go to the yield. So now, so the thing is that if you check here, so we have given that the conversion is same, 92% conversion. But if you want to use R yield reactor, then you should have you should have the data for the exact yield of each component. Okay, but you don't have that data. If you have that data, then you can use directly, but if you don't have that data, then you first run the R stoichiometric. From the stoichiometric you will know the molar flow rates, then you can use R yield, or you can do some calculation, theoretical calculation, and you can find the composition from those calculation, and you can enter in the R yield. So here from the R stoichiometric, if you see the yield basis, then from the mole fraction, the mass fraction will be this. Okay, you can check this data from the stoichiometric reactor results. So we know the data, just enter, like the CO will be this. So if you want to see, you can go to the block B1, then the stream results. So if you go to the mass fraction, so yeah, here you can see that the steam is 0.622443, CO is 0.0189761, like that only. So you have all data, your mole fractions, your mass fractions, so you can choose any of these data, and then again go to the yield reactor, and you can check here the basis, mole or mass. You can choose mass, then enter the correct yield. Okay, so you can enter these components, and also there is option like so there is the yield option. So we have component yields. If we know the components, there are some more options are there: user subroutine, component mapping, petro characterization. So you can have you have multiple options here. For these options you can refer to the manual. In user subroutine, I think you can define your own code. So you can define your, like if you have some custom model, so that will be useful in that actually. So you can define that this will be the yield from this reaction. So you can use some like your customized thing. Okay, so these are the input for the yield reactor. Then just go to the results. So now let's also make it to the stoichiometric. So yeah, so we can compare. So we have both the yield results and the stoichiometric. If you see, so they are nearly same, because we have given only the same data from the R stoichiometric to the R yield reactor. Okay, so they are almost same. But if you also see, we have a warning here, okay, in R yield, because R yield based on the mass balance. Okay, so it will do the equal mass balance for input flow and output flow. Due to that, there is warning. So it will like if you click on the warning message, if you want to see the warning, then go to the results status. Yeah. So the specified yields have been normalized by a factor of 0.9999. So this factor is used to normalize the mass balance. Okay. So you can have this kind of error in R yield. Now, if you go to the next reactor that we have is the equal reactor, R equal. Okay, in this reactor, you can see we have two outlets, one for the vapor and one for the liquid. So if you know that there will be, so it's easy if you know that there will be like two phases and you want to see them exactly, then you can use this. So here also the temperature, okay, valid phase, vapor, liquid, both, then the reactions. So we have already defined the reaction. So here it's already using the reaction one, okay. Click edit. So here we have two options like temperature approach. So you can use the temperature approach. You can extent estimate. If you have given some extent estimate, then you can use that, or you can use temperature approach. So we have given in question, the approach is 253 degree. Okay. So you can use that temperature here, but this temperature is like if we 253 degree you can choose, but this is the exact temperature to get the dead data. So you can find the exact temperature from these all reactors. Okay, so just you can enter the temperature that is you given in the question. Okay, so other options are also there, like convergence, maximum iterations. So you don't need to enter in these, but you can, if you like do advanced modeling, then maybe these options are useful. But as of now, we only see the specification reaction, they are useful. If you go to the result, then this is the which one? It's the model number B8. So yeah, stream results. So see, so we have L equal, V equal to liquid phase, vapor phase. So we can see that. So there is no liquid. So liquid phase, there is nothing. Okay. And we have in the vapor phase only. Compare the results with the stoichiometry. So it's near, because initially you have mentioned that 253 degrees standard temperature approach, but from the calculation we can optimize that, and we know that 246 is the temperature that will achieve 92% conversion. That's why we use that. Okay, and if you want to do that, then you have to go to sensitivity analysis. So left option you can see the model analysis tools. Okay, here you can see the sensitivity. Then here, if you want to check the exact temperature at which you will get, you will, like, if you are using temperature approach, then if you use that temperature, then maybe the conversion is or 90% only, or 85% or 95%, but you won't have 92% conversion. So from the stoichiometry or R yield, you know the data. Okay, so from that we will try to, or from this also we will try to see the yield of like a component. So if you see here S1, so we have defined a variable S1. Okay, so it's a variable, then it's a block variable, because we want to see, we want to vary a unit operation block. Okay, so it will access a unit operation block and it will change a particular parameter. Which block? B8. You have to specify your block number. You can also name, rename those. So be careful with these when you use this. So main flow sheet. So you see it's B8. So that's why we have to use B8 here. Then the variable, which variable you want to select to vary. Okay, so if you click on it, so if you find like approach here, so you see the temperature approach. So this is the variable. So actually this variable in the like this is visual interface, like interface for the Aspen, but in background it is having some calculation, as we discussed in our previous classes. So it defined the variables and all things. So this is the variable that Aspen defined for the calculation. So if we want to optimize it, then we need to know the variable name, so that the equation behind the models will optimize that particular variable that is required. So here that is the delta t, del t. So click on that, then give an ID, then units. So it is in degree or like that. So it's in degree. Then here you can see the manipulated variable limit. So you can manipulate the variable. So like you can start or end point, you can mention the start point and end point. So you can, like, if you know, like you can mention 230 to 260. So it will give you result from 230 to 260, and you can mention the increment and all. Okay. Then you can define it further, like which stream you want to, then like we want to see the composition of the stream. Like if you want to know the like amount of CO2 in the product stream. Okay, so you can use the stream and you can define mole fraction, which stream. So V equal is the output stream name, then it's mixed stream, then component CO2. So we have defined, like we will see the if we vary the temperature, then we want to see the change in the CO2. The meaning of this is that, so first you have defined the variable that you will vary the del T variable for the R equal reactor. Okay, then you want to see a variable which will change. So you want to see the stream data, and which data? The component, the CO2 component. We have like these components, but you can select any component, okay, CO, CO2, but you want to see the CO2. Or either you can also select the CO and all. So for this, we have selected the CO2. So now if you select it, then go to tabulate. So it will tabulate uh, the variable one, okay, and it will give you the result. So if you see the results here, then you can see here. So see, for like I have mentioned to 46.5 to 47.5. Okay, so see, so it's changing the temperature from 551, 52, 53 like that to 46.53, 0.54, 0.55 like this. And you see the mole fraction is changing like this. Okay, so now you can compare this mole fraction with the R stoichiometric, R yield, or you can find like this temperature is the temperature at which your system will achieve the 92% conversion. Am I clear? Okay. So now if you want to see the Gibbs-free reactor, then you can see here it's a Gibbs reactor. So here also you can see the Gibbs-free reactor, you can mention like different things like calculation phase equilibrium, okay, phase and chemical equilibrium. So these kinds of things you can choose. So like here we have chosen the phase equilibrium and chemical equilibrium. Okay, you have defined the pressure, temperature. You can also define the heat duty. But if we have defined this temperature, okay, then it's include vapor phase also. And here you don't need to specify the reaction. Okay, it will show you all the phases. So here you see the R Gibbs consider all component as products. So it will specify, it will take the all component as product, and there are more other options. So you can also go through more other options through the manual. Okay, you can read about this. So if you compare the results, so see, so the if you see the H2O, then let's see the mass flow actually. Yeah. So from stoichiometric, we get 185.461 kg per hour, but from Gibbs, from the total equilibrium calculation, we can get up to 199.018. Okay, and you see, so like CO2, the output is 4048, but here 4344. So in this way, you can compare all the P Gibbs P regarding the yield and all. You can compare all the data. Okay, so let's go to the flow sheet again. Okay. So this about the reactor, and we are also have the CSTR, R plug, and R batch. So in these also we can do some. We can have some other parameters. Let me go to the PPT. So now, like for the common reactants, if you have given the kinetics, so here like we have another question. We have given the kinetics actually. So you see, you have given the like power law, like you have given the kinetics data, the forward K reverse. Okay, you have to use this law, and you have given the for CSTR temperature, pressure, vapor liquid phase, their volume. For the plug also, you have mentioned all the details. You have mentioned the method. You have given the inputs. Okay, and you have to make the CSTR plug and batch reactor. So let's quickly go through an example. system is slow. Sometimes it takes time. Okay, it is the same one. Okay, just give me a minute. Okay, we can see quickly here. Suppose if you just take the CSTR, R plug, R bench. Okay, so this because we have already know how to do the calculation of this, I want to just quickly go through the options that are available. So if you go to the CSTR, then you can see here you need to specify the temperature. Like you have two types, like model fidelity, conceptual, equipment based. So if you have more data, then you can use the equipment based, then kinetics data and all. You have to give here the vessel data. Okay, but for the conceptual mode, you don't need to give the vessel data, but still you need to give the kinetics data and all. So if you go to the question, then you can see we have given some data. The temperature we have given, the pressure we have given, vapor liquid phase, and we have given the volume. We have given, so we can first we can define this data in our compound specification, then the property, then the simulation window. We will select the reactor, and we have these inputs. Okay, and these are the kinetic data. Quickly go through. So this, so here we can specify the temperature, we have specified the pressure. Okay, so see, the pressure is mandatory. So for operating condition, you can see the you cannot this is default. Actually the pressure you need to select it, you will define the pressure. But if you don't have temperature, you can change, you can define the duty, you can define the vapor fraction. So you have three options. Okay, suppose if you have a duty, so like this reactor will use like 10 kilowatt or like 1 kilowatt of heat. Okay, so it will automatically calculate the temperature based on that. But here we have given the temperature, so you can define temperature, but pressure is mandatory. Then the phases, then vapor only, then reactor volume. So you can specify the reactor volume, the residence time, okay, the reactor volume and phase volume. So you have multiple options here. So here we have given the volume, so you can define the reactor volume. Okay, you can define the volume here. So you have option for liter, ml each. Okay, then go to the kinetics. Then here you need to define the kinetic parameters. So just go to the new, because we have don't have any reactions here as of you can see now. Just go to the new, then let R1. Okay, reaction 1. Then what kind of reaction is it? Okay, so we have different kind of reactions. So like emulsion, free rate, general, power law and all. So this one is given the power law. So go to the power law. Okay, so now you have reaction R1 here. Okay, but you have not defined the reaction R1. Then you need to go to the reactions here. Okay, so go to the reactions, then go to the R1. Then here you can see the input is required. So here you will define the reaction. So see, you can define the same, the reaction you can define here. Okay, then you can choose the component, like these components are here. Okay, suppose if we again take the water gas shift reaction, then it will react with, you can see the water will be react with the CO. Okay, then it will result in the CO2 and H2, and coefficient is, okay, Okay. So here you can now you need to do into the kinetic parameters. So you have given the K value. Here you can enter the K value. Okay, you can enter all the values that you have given for that kinetic parameters. The reacting phase you can mention, the rate basis. Okay, so like volumetric or weight basis. Okay, so you can see this, and we have given the data here. So you have given the E value, the K value. So it's actually, you see this sign. So maybe this reaction can also happen in the reverse manner. So you need to, when you're dealing with the reaction kinetics, then there are many parameters. Okay, so you need to define both forward and reverse direction. So it can go into this direction and this direction also. So the direction will depend on like pressure, temperature, and like these energy and all these data. Okay, there are more data, so you can go through more about the reaction kinetics. You can learn more things about these. So the kinetics is very important. Okay, so you have this formula. You can find, you have given these values, so you just need to put it, and you can just run it. It will give you the result. The important thing is here that sometime you don't have these old data. Okay, this K value and E value, but you have some like basic data, so you need to find these data K, and you need to calculate these coefficients. Okay, so you need to use the basic reaction kinetics formulas and the basic data available with you, and you need to calculate it. Sometime it will be given to you, and sometime you need to calculate. But when you are using the CSTR reactor, then the kinetic parameter is important. You need to know these data. So these are the options for here. So again, go to the flow sheet. Like for the plug flow reactor, so you can specify the type, like you have different options: adiabatic reactor with co-current thermal fluid. So you can specify different kinds of the reactor type. Okay, let's say adiabatic reactor. In the configuration, you can define the length or diameter. Okay, so if you have the length and diameter, it's good. Like we have given here, the reactor length is 2 meter, dia 0.3. So you can mention that. You can check the vapor and liquid phase. So here, see it will be vapor, and you need to change it vapor and liquid. It's important. So these things are important actually. Okay, so again, the reactions we have already defined. If R1, if you have already defined the reaction, then it will directly come here. Just select it. Okay, so suppose you are doing a complex modeling in that you have multiple reaction, and a particular block need only two reaction. But in your system, in reactions, you have defined 8 reactions. So you can select. Suppose at this here will be like more reactions, so you can just select and click this. So now only this reaction will take part for this particular block. So you can do that. So now let's take the batch reactor. So in batch reactor, you can see the specification, temperature specification. You can define the constant temperature, profile, heat duty. Okay, there are multiple options. Then the reactor. Okay, the phase, liquid only, vapor, liquid. So we have given something like vapor, liquid, stopping criteria, mole fraction of ethyl acetate, total cycle time 1 hour, calculation time 5 seconds. So we have given more data here. So you will find like kinetics, we have reaction, we have given stop criteria. So here you have to specify the stop criteria. The time, then cycle time you can specify here. We have given the question, times in question and all. So you can specify these things here. So these things are about the reactors. So we have covered stoichiometric yield, equal Gibbs, RSTR, plug and batch. Let's go back to our slides. So we have also covered pump. So in pumps, we need at least one input, one output. Then feed must be incompressible fluid, liquid phase, and may also be used as turbine. So the pump can also be used as turbine. Then pressure ratio, we can enter the pressure ratio. Okay. If you have the exact pressure, you can define that. You can also mention the pressure ratio. Like suppose you need 3 or 4 pressures. Like if your input is at 5 bar and you apply the 4 pressure ratio, then it will be like 5 multiplied by 4. Power requirement is calculated. So with this data, you can calculate how much power is required to run that pump. Or if you are using as a turbine, then you can find out how much power this turbine will generate. Similarly, for compressor, there at least one input and one output. Okay. So excellent in pressure increase in gas phases. So if you are dealing with the gas phase and if you want to increase the pressure, we can use the compressor. Because now further from this week, we are going to see the complex examples of complete systems. Okay, in which there will be multiple BOPs like balance of plant equipment and all. So we'll do the modeling of these things. So in that we have to also use compressor, pumps and all. It can be also use turbine, pressure is allowed, performance curve. So basically, for the compressors, we have different data, like how the efficiency and all is how the performance, because sometimes the performance will change with the pressure ratio, with the flow rate and all things. So if you have the curve, then you can use that curve. You can enter that curve in the modeling part, and the results will be as per that performance curve. And the Aspen also have some built-in compressor models from some vendors. So they have already defined their curves, so you can directly select those also. That is a basic example. So here we have given a water, then pump we have given the efficiency. The globe wall we have given an opening, 50% opening, then we have given a pipe. Okay. We have given the performance curve here or an efficiency curve. You can see the change in the flow rate with the head. Okay, so you can use this data to model the pump, and you can also use this data for the efficiency calculation. So we will go to this example if time permits. Just move forward for the questions. So now further the example of turbine. So we can also use a isentropic turbine. Here the steam flow rate we have given, and the steam outlet we have given. Okay, so we can just we know the flow rates, we know the data, we have the model palettes for the compressor. We can use this and we can get the result. So if you don't have the if you have efficiency, isentropic efficiency, it's good. If you don't have the efficiency directly, then you can find the turbine efficiency like isentropic work and the actual work. So it will be the isentropic efficiency. Okay. So if you don't have the exact efficiency given, but you have given the rough data, so you can find the actual efficiency from this calculation. So this is the complete flow sheet, the process flow sheet. So as of now, we have covered multiple unit models. So now we are connecting all those units together. Okay. So this is the complete process flow sheet of a hydrocarbon plant. So here you can see we have inputs. We have given some hydrocarbons, methane, ethane, propane, butane, okay, benzene, toluene, like that. So then we use a heater to heat it up. Then we use a flash chamber, so it will change the vapor phase, the liquid phase. Then this phase is further go to the combustion chamber. Okay, and we have also have air. Then they will go to the combustion chamber. Then they will combust. The combustion will be there. It will release some heat. You can check that. Then you can go to the exhaust. You can see the composition for that. Then you can use a valve here. Then again a distillation. So it's given rigorous calculation. You have given all data, number of stages, feed stage, okay, the condenser pressure, reflux ratio. Then again column 2. So here we have product. So then this product from the column 2 will go to the pump. Then similarly from column 1 it go to the compressor. It will generate the LPG. So this is a complete flow sheet. Okay. So as of now we have studied the unit models, but now we will connect all these unit models and make a complete plant model. Okay. So we will look into this at the end of this class. So first, like the task for this flowsheet is like develop a steady state model for the plant using Aspen. So you will develop with this data, then the verify material and energy balance of the unit operators and unit process. So the best thing to do this complex modeling is that do step by step. Okay. First, define all these components you have, then define the heater only. Okay. Just input and output, then run it. Then check, is it okay or not? Is there any warning error? Okay, everything is fine. Then put the flash chamber, then connect two streams, then again run it. Then again check if there is any warning or like any error or it's running fine. Then connect the wall, then connect the column one, then run it. Then again connect the isentropic compressor and run it. So go step by step. Okay, then only you will make a good complete flow sheet without any warnings or error. Because suppose if you connect all things in one go and then you run it, okay, so then it will be very difficult to find. If you have any warning, then it will be quite difficult to troubleshoot that warning, okay, or that error. So it's better you should run each model, then connect sequentially, and at the end of all the connection, just run it. So these are the questions you can do in, I think it was discussed in the class also, decrease the heater temperature, discharge pressure of wall. Okay, so it's discussed in the class. So if you want to go deeper into this, you can refer to the class videos. And at the end of the class, we will also go through shortly. Okay, so let's start with the assignment questions. So the first question is, our stock block performs product selectivity and heat of reaction calculation. True or false? Take 2 minutes or let me know the answer. Let me reshare my screen. Okay, just a minute. Yeah. Okay, yeah. Anybody?
It's true.
Okay. Let's wait for some more answer. So if you have Aspen open, then you can just go to the Aspen and you can check that. What are the options available there? Quickly go to the Aspen directly. You can check that there also. Okay, it's true. So selectivity means you can define the conversion for like component. Okay, so basically you can define the selectivity, and heat of reaction calculation is also is the part of our stock block. It's true. So our yield block needs stoichiometric information and it performs heat of reaction calculation. True or false?
It's true.
Okay, let's see. Anybody else? So it's false. Why? Anybody?
First law of thermodynamics doesn't hold true for this.
Yes, yes. Anybody else?
It does not perform heat of reaction calculations.
Yeah. So because it does not perform the heat of reaction calculation, it doesn't follow the first law of thermodynamics, so it's false. We need to know the yield of output. Okay. So basically we are giving all the information to the block itself that this compound will be this much, this will be this much. So we are giving all the information basically. Okay. So the vapor figure 1 is a snapshot of the main flowchart of a simulation run. Answer the following 3 questions. So you can see a snapshot. So here you can see the temperature is like this block, pressure, mole flow rate, and mole vapor fraction. You have given data here, these things. Okay. So now calculate the vapor flow rate in the feed S1. What is the vapor flow rate in feed S1? Let me know.
300.
But 300 into 0.87.
I think your answer will be rejected because if you type this answer in the system, it will not accept it.
No, actually, means I'm just telling the mathematical expression.
No. Answer. So we have one answer like 300. So anybody else? Let's calculate it and let me know the answer. We have one option as of now. We have one answer 300.
So 261 kmol per hour.
Yeah, nice. So we have two answers. One we have one we have 300. So I think you directly check the flow rate.
0.87 to 300.
And I think
261.
the other answer is 260. 261 point something. Okay. So the question is vapor flow. Okay. And you have given the molar vapor fraction. And this is total flow. So the 300 is the total flow, not the vapor flow. If you want to calculate the vapor flow, you need to see the vapor fraction. Okay. So be careful with the question and the information. So the correct answer will be 260.262. Just multiply 260 to 262. This is the range. So the 261 point something is the correct answer. So just multiply 300 with the vapor fraction. Molar vapor fraction is 0.87. You will get this answer. Now, what is the pressure drop across the system? So you have given a system, and what is the pressure drop?
0.
0.
0.
Why 0?
It's constant at 35 bar.
Yeah. So basically, if you want to see the pressure drop, then see the pressure at each like input, then the output, then again the output. So the pump input is 35, output 35. The reactor input 35, and output 35. There is no pressure drop. Okay. So it should be 0. The block B1 is a cooler. True or false?
False.
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 Why?
Temperature is increasing.
Temperature is increasing. It's a heater.
Yeah. So the temperature is increasing. You can see here that it's was inlet at 230 and the outlet is 360.85. So temperature is increasing. So suppose what will be the heat duty? Will be positive or negative?
Positive.
Okay. Anybody? You can try it in a just Aspen? Should it positive or negative?
Negative heat is given to the
Okay, try it and let me know. So this is false. The block B1 is a cooler. False, because here we can see the temperature is increasing. Okay. So basically we need to give the heat. Okay. So you have to check if you are giving a heat to the heater, then the duty should be positive or negative. Check it and let me know. And also try this question. Okay. So the question in I think in this you have to apply the heater, then you can check in that actually. So the question is a fluid mixture of 100 kilomolar toluene and 100 kilomolar hydrogen at 200 degree and 30 bar pressure is being heated to 700 Kelvin through a heater and thereafter being fed to the stoichiometric reactor based on 90% conversion of toluene. You have given the reaction, you have given the reactor, which reactor you have to use, you have given the conversion, you have given the input. The reactor operates in the vapor phase and there is no pressure drop across the entire process. And the SRK property method may be used. You have given the property method. Answer the following 5 questions with accuracy. So just make this model quickly. So all the question is after based on this only. So take approx 5 to 7 minutes. Just quickly make this model in the Aspen, and after that we will discuss it. So take 10 minutes at least. Okay. Be careful with the input information. Be careful with the units. Be careful with the methods.
Excuse me, sir.
Yes.
Sir, I'm facing some issues in downloading the software. I had filled that Google form regarding query twice, but there's no response. So my
Okay.
assignments are being delayed. So what should I do?
So what kind of issue you are like facing?
Like I have downloaded it from the link. So now
Okay.
when I'm
Which
opening that
version? Which version? 12 or 14? Now I think they have
14.
released 2 version. Okay. Okay.
When I'm opening that folder, the setup option is not there as it was mentioned in the installation document.
Okay. So have you extracted all the files correctly? You need to extract all the files first. I think the download will be in the zip file. You need to extract all the files to a folder. I think then the setup option will be there. And I think there are multiple files, I think. So you need to download all the files.
one more input, please. There is a separate setup file to download. Did you download it?
Yeah, there are multiple files. Yeah.
There was one link, I have downloaded it.
No,
And
the link, one link has got the Aspen 14 files, and there is a separate link for a setup file.
Yeah. So please look into it. I think there are multiple links or there are more files there. So go through that carefully. Okay. Go through the mail again. Maybe you will look into deeper. You will find the information. Yeah. So let me give you some hints. Okay. Anybody is having any answers as of now? Okay, just wait for 2-3 more minutes, then I will start. So the first thing you need to define the components. Okay. So you can see the components will be these four. Okay. So because this is the reaction that is taking place, so you need to define all these four components and define these components first. The second, you need to choose the SRK property method. If you are using SRK, then I think you need to use steam NBS. Okay. If you don't use, I think you will also see a warning that you should use it. So you can check it. If you're using SRK property method. Anybody, any answer? Are you facing any problem?
I have a doubt. Is it necessary to use version 14 of the software compulsorily? I'm using
Sorry?
version 12 as of now.
Sorry, please repeat.
Is it necessary? Is it compulsory to use version 14 of the software, or
No,
version 12 is sufficient?
No, yeah. You can even do it in version 10 or like 7, no issue. This is the data.
Okay.
Yeah. Version is not important. The data
Because
has given you.
some of the properties might have been updated. So that's why I'm
No.
asking.
It's a very simple question, so it's not that will create that issue. Actually, if you go towards complex problems, then this will do some minor changes. But normally, it doesn't change that much.
Okay, for this course, any version is okay, right?
Yeah. Okay, do we have any answer, or should I start? Okay, is anybody trying or not? Let me know. Anybody? Last 1 minute.
0.69.
Okay, we have an answer. So 0.69. Anybody else? Okay, let's see. So you can see first in the properties, we have defined the hydrogen, toluene, benzene, and methane. Because if you see here, so these are the components that are included in this reaction. So you need to include all these components in your properties. Okay. So we have taken hydrogen, toluene, benzene, methane. Then method. So we have to use SRK. Select SRK, and if you select SRK, then you need to use the free water method as steam NBS. Okay. If you don't use it, I think Aspen will also give you some warning regarding this. So steam NBS is the best method with the SRK. So first we have specified the components, then we have chosen the method properly. Okay. Now we have given that the fluid mixture, we have given the flow rates at 200 degree and 30 bar is being heated. So whenever you have a problem, then go step by step. So first you have a feed. Suppose you have a feed. Okay. then this feed is being heated. So then there will be a heater. Okay, it is at 200 degree. So whenever you are trying to do a problem, make a rough sketch. Then 30 bar pressure. So you have this data. So it is being heated to 700 Kelvin. So this will be the output stream. So it will be 700 Kelvin. And there is like no mention of pressure drop. So you can consider it will be also 30 bar. Okay. So the important thing is that, see here, the inlet is in degree, it is in the Kelvin. So be careful with this data. Okay. So you need to be careful with the temperature units also. Okay. Now this further goes to the stoichiometric reactor. So this feed will go to a reactor. So in this reactor, this equation is working. You need to specify this equation for this reactor. You need to specify the conversion. Then you will get a outlet from this reactor. So our questions, next questions will be based on all these data. The first question is the molar vapor fraction of the feed, because you see that feed is at 200 degrees centigrade. So it is more than 100 degrees centigrade. Okay. And we have different kind of components. So we don't know. So the temperature is high. So we don't know the exact the boiling point and all the properties this for this component. So it is better to check the vapor fraction. Okay. So we can check that from the after the specifying the properties and the feed stream. If you go here, so we have specified the property, we have specified the components, then go to the simulation. Then here just make a heater, then connect stream S3 inlet and S4 outlet. Okay. So suppose I think I can deactivate it. Deactivate. Okay. So now I have deactivated this reactor. So now only this heater will run. So let me check. Okay, so yeah. So it's good option actually when you have a complete flow sheet and you want to check, like if you are having any error in particular section, so you can deactivate the further section. Okay, so I want to see only the heater. I have calculated all things, but I have just deactivated this section, the stoichiometry reactor and this stream. So right click and there is option activate and deactivate. So you can click on deactivate. Okay, so now only this your input stream S3, your heater and output stream is working. Go to the results, the stream results. So input is S3. So here you can have the vapor fraction. Yeah, vapor fraction. So you can see the molar vapor fraction is 0.698967. The temperature 200, pressure 30 bar. So you can see here the vapor fraction is this. Now let's see the answer. So yes, the answer is 0.68 to 0.71. So the correct answer is correct. Now what is the mass flow rate of benzene at the reactor outlet? So now you have to tell me the mass flow rate of benzene at the reactor outlet. Let me know the answer. Mass flow rate of benzene at the reactor outlet. So basically, this is the outlet of reactor. So what is the flow rate of benzene at here?
$7030.
We have an answer 7030. Anybody else want to answer?
0.23.
Okay. Okay. Yeah, actually it's better because 7030.23. So it is mentioned here, answer the following 5 questions with accuracy up to 3 digits after decimal point. A very important point, because in this type of question, if you don't write exactly, because they have their particular range, so if you only write 7030, or maybe the range is started from 7030.20, then your answer will be wrong. Okay, so be careful with these things. Let's see. So now I want to see the result of reactor also. So right click, just activate it. Then this stream, activate it. Okay. So now both are activated. So the flowsheet is complete. You can run it. Okay, no warning, results available. And go to the stream results. So we want to see the benzene. So the stream is S4, then the mass flow. Okay. Is it not working? Okay, it is S2. S2, stream is S2. Yeah, S2. So stream is S2. So go to the mass flow. The benzene is 7030.23. So this is the correct answer. Okay. Yeah, see, range is 7030.22 to 24 only. So be careful. Okay. The heat duty of the heater is, yeah, the duty of the heater. Now you can know that it will be positive or negative. You can see the from the Aspen actually itself, because here we are heating it. So Aspen will give you the result in correct format.
1847.66.
1847.66 kilowatt. Positive or negative?
Yes, sir. Positive.
Positive.
1847.66. Positive.
Okay. Anybody else? Okay. So let's go to the heater. Yeah. So yes, so we are the heater results. So heat duty here we can see kilowatt. So it's positive. Okay, because we are giving heat. That why it is positive. Its heat is given to the heater. Okay, so this heat will be like you are adding this heat. Okay, so you can also check the balance here. So if you click on the balance, then you can see the in and out. So you can see the mole balance, you can see the mass balance, you can see the enthalpy balance. The phase equilibrium, you can see the phase equilibrium also. Okay, so there are options to see the data here. So let's go to the next question. The correct answer is, sorry, yeah. So it will be negative actually, yeah. So let me remove it. See, yeah, it will be negative. So that was my question, because I know the Aspen will give you the result in positive. So don't see here, it's positive. But in actual, it should be the humidity of heater. So we are adding heat to the system. So we need this heat actually. Okay. So minus 118.96.
I got in
Or-
negative.
Sorry?
I have got it in negative minus 1204.85.
Okay, your answer is negative. Let me check in
Yes.
the Aspen why we are having some positive answer also. In my, I am also getting positive. Why? You are getting negative.
Yes, sir. Yes. But a
Okay.
little different. 1204.85. It is
1, 2?
04.85.
No, I think you need to check your other data actually. Yeah. But why? But we are getting in positive. Actually, I think we have already in class 1 we did some a heat exchanger calculation. Okay. So we can go through that, and I will show you at the end of this class. I think I have that file with me. So but it will be negative actually. Okay. So 1188.96. The volumetric flow at the reactor outlet. In meter cube per hour, the volumetric flow at the reactor outlet. Anybody?
Three 380.767.
380.767. Yes, answer is correct. If you go to the Aspen, then you can see the stream results.
Peak added to the system due to is negative, right?
See, how much? What was the flow rate of?
Volumetric flow, sir. Last line.
Volumetric for reactor outlet. Okay.
Bottom में sir. Bottom में.
कहाँ पे गया यार दिख नहीं रहा. Yes, yeah, here it is. Yeah, okay. Yeah, volume flow, yeah. So 6347. I think this is the S2 or S4
Unit change, sir. Unit change करना.
Yeah, unit. You have to change the unit also. Meter cube per hour, cubic meter. What is the unit?
Meter cube per hour.
Yeah, cubic meter per hour. 380.858. The stream is, let me check, S2. Yeah, S2. So here the stream is S2, 380.858. Yes, 380.858. Okay. So this is the way to do the question. Let's see other questions. So reactor simulation may be performed by red frac +3 R equal R Gibbs. Anybody?
R equal R Gibbs.
R equal and R Gibbs.
R equal and R Gibbs. Okay. the equilibrium based model equation are used in?
R Gibbs.
Okay, and only R Gibbs? Anybody?
Plug and batch also.
Only R Gibbs. Because the equilibrium, it will do the both chemical equilibrium and thermodynamic equilibrium. Okay, or phase equilibrium. Chemical phase equilibrium will do the complete calculation. So the R Gibbs is only reactor which do the complete equilibrium calculation and also follow the first law of thermodynamics. Our stoichiometric block can run either simultaneously or sequentially.
True.
It's true. Okay. Which of the following is our pressure changer model block in the Aspen plus simulation window? The pressure changer.
Multiple compressor, M compressor.
You can see the model palette in Aspen just quickly.
Pump and M compressor.
Pump
and
and
M compressor.
M compressor. They are the pressure changer models. So a pump has been specified as shown in figure 1. Next two questions are based on figure 1. Okay, if the discharge pressure is 20 bar as shown in figure 1, the inlet pressure should be space bar. We have given the pressure ratio here.
5 bar.
Will be
5 bar. 5 bar.
5 bar. Because discharge pressure is given, just divide it with 5. If the efficiency of the pump and its driver are 70 and 90% respectively as shown in the figure, then the missing data at A and B are space and space respectively.
0.7 and 0.9.
0.7 and 0.9.
Yeah. So basically, because the point of this question is that here you only mentioned the efficiencies and only the pump and driver, but you have not mentioned like either it's percentage or fraction. That's why the question is that when you have efficiencies, you need to enter it here in fraction format. Okay. A turbine converts kinetic energy to the electrical energy.
Thermal energy.
True
Thermal
or
to
false?
electrical. False.
False.
Okay. So turbine converts, what will turbine do then? Anybody? If it is false, why it is false? Anybody?
So steam at superheated stage
Okay.
will impart its whole energy to the shaft of the turbine, and therefore it will rotate. And thereby it will
Okay.
get saturated or condense, or
Okay.
maybe just above superheat temperature.
So as you are saying that you are supplying the steam that is driving the turbine and
Yeah.
you are having mechanical power.
Yes, sir.
Okay. So what that mechanical power do?
Generates electricity.
Yeah, generate electricity. So that what turbine then turbine converts the kinetic
It will
energy to
be
electrical
true,
energy. True or false?
True.
Why true?
Because
What
steam
turbine
has
do?
kinetic and
Yeah, steam
the
has
steam has kinetic energy only.
yeah, steam has kinetic energy. Okay. And why steam has kinetic energy?
Because the molecules are in random motion.
Because of high temperature and pressure.
Temperature activation.
Yeah. So temperature is very high. If you increase the temperature, then what will happen? If you are having steam, let's say I have like 1 liter of water. Okay. So if I convert that 1 liter water into steam, then can you tell me how much steam I will get at like at STP at 100 degree or at 1000 degree? Anybody? Can you tell me? Just quickly, just calculate. Just quickly. Suppose I have 1 liter of water, and if I want to convert it to steam, then what will be the quantity of steam at STP, like the standard condition, okay, or 100 degree, and at or any other temperature, maybe suppose 800 degree, like that. What do you think? A random number, just guess it. Make a guess. If you want, if you are able to calculate, just quickly calculate or make a guess.
Sir, volume is around 1500 times, 1500 times the volume of liquid. So maybe 1500 liters.
Yeah. So at what temperature? The temperature is important actually. If you are
At
saying
100 degrees.
1500 times, it's good. But 1500 times at what temperature? Because the temperature plays very important role in the volume. So when you are saying 1500, then you need to also specify the temperature for that.
100 degrees.
Temperature will be 1500 and means the same
1500.
temperature only.
Sorry? I'm not getting your
So
point.
initially, what value did you say for temperature?
No, my question is that, let me write it down. You have 1 liter of steam, sorry, of 1 liter of water. Okay. So at STP. So you know the STP condition? Are you aware? What is the STP? Anybody? What is the STP? Okay. STP,
273 Kelvin, 1 atm pressure.
yeah, 273 Kelvin or 0 degree and 1 atm. So I have 1 liter of water at STP. So always remember, when you give any data, like any flow, you need to specify these conditions. They are very important. Okay, normally we tell direct like 1500 ml, but 1500 times. But what? Because it's very important, because the specific volume, the volume will change with the temperature. Okay, so it is not same at each temperature. So now I want to know the amount of steam, like approx amount of steam at STP at 100 degree or at maybe 800 degrees centigrade. Just quickly tell me. So you, one of you said 1500 times. So at what temperature? Either it at STP or 100 or 800. Because it's a huge difference. And the pressure is 1 atm. Pressure also play important role. So when I'm saying that 100 degrees, so I'm also wrong actually. I need to also tell you the pressure, because at STP I'm telling you the pressure, but at 100 degree mean 1 atm 100, 1 atm 800. This is the correct way of saying. Now let me know the amount. Just quickly, 1 minute. Anybody? Roughly you can just rough calculation. Not the, you don't need to be exact. One of you said 1500 degree. Please, do you want to explain it?
Sir, usually the volume of steam is around 1500 times that of water. This is like thumb rule, but I haven't
No,
calculated it yet.
thumb rule, but okay, thumb rule is fine, but at what temperature? You need to know that.
Okay, sir, I'll look into that.
So thumb rule is that if you are talking about water, then you are correct, or almost there actually. So normally water boiling point is 1 atmosphere. What is the boiling point at 1 atmosphere? 100 degree. So when we are talking about the thumb rule, okay, so you need to also know the temperature and pressure. So for thumb rule, the temperature is your thumb rule, not the standard one. The pressure is 1 atm and temperature 100 degree, then it will be around 1500 times. Exactly, I think 1571, or you can do the calculation around 1500
around
times, you can say.
1600.
Yeah, so 1600 like that only. So roughly 1500 to 1600, you can do the calculation, okay? So, but if you calculate at STP, it will be 1241 times. If you go at 800 degree, it will be around, I think, 2700 times. So see the difference. So it's the huge difference, okay? From zero, like from STP to 100 degrees, see the difference. Then from here to see the difference. So the temperature is play a very important role. So if we are using the steam turbine, so basically we are at superheated state. So we increase the temperature. So if we increase the temperature, it means that we are increasing the specific volume. So now we are increasing the specific volume, then there are more molecules of that steam actually. So they will have their kinetic energy and they will rotate the turbine blades. And turbine blades will rotate. Then you have what kind of energy? The kinetic energy. And if you rotate, then you can put a dynamo there, you can generate the electrical energy. So it's true. The turbine converts the kinetic energy to electrical energy. Okay, it's not false. Anybody is having any doubt regarding this? Anybody?
Sir, sometimes turbine can be directly coupled with another drive, so it is not producing any electricity as such. So basically, it is converting kinetic energy into rotational energy. That's all. At this stage, we can say, unless it is coupled to a generator, it doesn't generate electricity.
That's correct.
So
Actually, that's correct. But normally, like the turbine, so suppose so. What is the purpose of turbine actually in general way? Because the question is not the basic question is that basically we are converting the mechanical energy, and mechanical energy is converted to electrical energy. So that is the correct way. But generally, turbine. Why do we like use the turbines? Do you have any specific use of turbines that where we are only using the rotational energy and not generating electrical energy? Have you seen that anywhere? In terms of turbine?
In steam intensive processes, directly turbine is connected to compressors, pumps.
And there is no, you don't use any, like you don't convert that mechanical to electrical energy in the process?
That is mainly in case of
It's
power.
turbine-driven pumps and compressors.
Okay. So turbine driven pumps and compressor. So basically, if we look into like in the way, suppose basically like the question is it's not that specific, but if you also see in that perspective, like if you are saying like turbine driven pump and compressor, suppose if you don't have turbine, then how will you run that compressor or pump? You need energy or not, electrical energy or not?
Yes, sir.
Yes. So basically you are replacing, you don't want to give that electrical energy. That's why you are putting a turbine there. So you are basically using the turbine rotational energy to drive that pump. So but still you are using but that pump motor, the pump will require that energy. So now that is coming from turbine actually. So mechanical work is going, but generally the turbine is for the electrical energy. So look into that perspective. If it is like specifically not mentioned, then you have to look into that. Suppose if there are more options like that, mechanical, electrical, then you need to select mechanical first, maybe. But if it's only given the electrical, so yes, if you have mechanical energy, you can easily convert into electrical. Okay. So this statement is true. So this thing is very actually important. Actually, look into it more. So as you increase the temperature, the specific volume changes, and this will change a lot of things. So our yield block doesn't need kinetic and or sizing information. True, false?
True.
Okay, so yes, we don't need any kinetic information for our yield block. The Peng-Robinson equation of state with Boston-Mathias modification property method is represented by space in Aspen plus.
PRBM.
Yes, PRBM. R stoic block is used where reaction kinetics are known but stoichiometric is unknown.
False.
Yes, because for R stoichiometric, you need to know the stoichiometry of reaction. How many types of reactors unit blocks are available in Aspen plus?
7. 7.
7. IAPWS stands for
Option C.
yes, International Association of for the Properties of Water and Steam. Okay, so these are the questions for today. Now let's go to the heater. I think we had a discussion there. Yeah. So heat duty. So as we are giving the heat to the heater, so it should be negative. Okay, but somehow I think I was also getting positive. So I have to look into it, but it should be negative. Why it should be negative? Because we are giving heat. Okay, and suppose if you are having a complete system, a complete process sheet, okay, and you do the energy balance. Okay, so suppose like as we discussed about turbine, so we are having turbines. Okay, so we are having other equipment, we are having a combustion chamber like combustor, and we are having multiple units. So Aspen can perform a complete energy balance. Okay, so sometime if you see the diagram, yeah, so if you see here, so a very important thing I want to tell you here is that so anybody, can you just quickly look into this flow sheet and let me know one thing, that how we can optimize it in terms of energy input. So first let's tell you one thing. What are the things, the units that require energy input? Just quickly, the major things that require energy input. Just don't in detail, just measure things. By the look only you can see. So the
Sir,
heater.
heaters and reboilers.
Heater.
Heater require energy.
Heaters and distillation reboilers.
Distillation actually a reboil require,
Compressor also.
but we don't know the exact detail about those. So just quickly we can see the heater will require energy for sure if you want to increase temperature. Then the compressor is also okay. Then the pump will also require energy. And which part will release energy? So we have combustion chamber here. So we are burning the remaining fuel from the flash tank to the combustion chamber, and we have exhaust gas. So what do you think? Do we have any system here that we are using this exhaust gas? Because suppose if you are burning this thing, then maybe the temperature will be around 400 degrees centigrade. So is it good to flare off this exhaust directly to the air with 400 degrees centigrade? Do you think is it optimized system, or we can use
No,
this exhaust heat?
we
So
can
it is
use
not
this exhaust is.
yeah, it is not optimized. That's what we can do in the Aspen actually. Now, if you check the system energy balance, then you have some info that yes, this energy you require to input the combustion chamber delivering this energy. So basically net energy like you required or you are generating. So you will have that kind of energy balance. But with the analysis, you can see here, you have heat available here. Like suppose you have, if you convert into the flow rate and all, suppose you have 50 kilowatt heat available here. So there is a potential of 50 kilowatt heat. Okay. So maybe this heat can be used here actually. So we can put a, instead of heater, we can put a heat exchanger. So we can supply this exhaust stream through a heat exchanger here and make it flare to the air from this point, and we can preheat this hydrocarbon that is going to the flash chamber. So we can eliminate this heater. So basically we can eliminate the heat duty required into this heater through this exhaust. Okay. So now what will happen? The requirement of heat will be gone. Okay. Are you getting my point or not?
Yes, sir.
Okay, yeah. So suppose in this heater, suppose you required 10 kilowatt. So now you have 50 kilowatt, so you can supply, you can use a heat exchanger. You can give this 10 kilowatt through this 50 kilowatt exhaust. So you can eliminate this 10 kilowatt. Okay. So now this 10 kilowatt will be negative actually, because this is we are giving to the heater. This 50 kilowatt will be positive. We are generating it. Now if we use it, then we will have a 40 kilowatt. Suppose if it is fully efficient, then actually it will be less than that. You can do the calculation. So that is the purpose actually. So the input will be negative or the that will be positive. Like turbine will give you the positive work. Okay, you can generate turbine work from 100 kilowatt, but the compressor will be in negative like that only. So this is the notation. But some of you also get positive in the heater. So I think we need to check the calculation again. I think we did some mistake there. So we will check it. So this is the thing actually. So now suppose if you still have some exhaust available, so the flow rate is suppose very high. The flow rate is, you can suppose say 100 kilomole per hour. Just suppose. So maybe you can put a turbine also. You have temperature, you have higher flow rate, you can put a turbine and you can give that to this compressor, the power. Directly couple the turbine with the compressor. Then you can eliminate the input energy here also. So in that way, we can optimize our system. So we can do the energy and exergy analysis. We can tweak the system design. We can tweak the system only in the Aspen, and first we can do the whole balance, then we can implement it. Like this pump also requires some input. So we can also see that we can get some work from this turbine. Suppose if you are putting a turbine here, we can also give work from turbine to the pump also. So this is the main, like a basic use of Aspen. As of now, we have only covered the unit models, but now we are moving towards a complete process flow sheet. Okay. So in further weeks, you will look into these things like how to optimize the system, how to do all these things. Okay. So I think we have covered enough for today's class. So this is my email ID. Okay. So if you have any query, you can write to me. So thank you everyone. So I'm stopping my screen sharing. Okay. So thank you for joining.
Okay, sir. Thank you.
Okay, thank you. So meet you again next weekend. Bye bye. See you.
Bye, sir. Thank you.
And sir, I'll try downloading again, and if I face any issue, I'll write to you in the email. So just please.
Yeah, okay. Actually, yeah, there is also a WhatsApp group. I think it's better to take help from the WhatsApp group also, because maybe there will be some other issues also. So, and you should also write to the NPTEL team and try to
I have
download the
already
files
written.
again. And I think there are multiple links for downloading. So suppose if you are facing any error with a particular link, so you can try some different link. So go through that, and I think it will be resolved.
Okay.
Okay. Okay. Thank you. Bye bye. See you.